Alright, the final lessons of permutations and combinations, lesson number 8. We're going to be looking at the binomial theorem. So last lesson we learned all about the expansion of x plus y to the power of n, and we also developed Pascal's triangle from them. So just a reminder, if we had x plus y to the power of 0, we got 1. X plus y to the power of 1, we had x plus y. X plus y to the power of 2, we had x squared plus 2xy plus y squared. If we kept expanding the binomial x plus y, we would get the following expansions. Now, one thing that's connected to these expansions is the use of Pascal's triangle. We see that the coefficients 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, and 1 they're exactly the same as the numbers in Pascal's triangle. The same goes for combination form. 0, choose 0 is equivalent to 1. 1, choose 0 is also equivalent to 1. Same as 1, choose 1, 2, choose 2, 3, choose 3, or on the other side, anytime we're choosing 0, it's always equal to 1. With Pascal's triangle, we take two numbers and add them together to give us the sum for the number below. So 1 plus 2 is 3. Or we could look at 2 choose 0, which is 1, plus 2 choose 1, which is 2. Add those together and we get 3 choose 1, which is equivalent to 3. So Pascal's triangle and Pascal's triangle in combination form work identical. So now we're going to explore the binomial theorem. Referring to the combination array and Pascal's triangle above, it is not just a coincidence that the combination symbols represent the numbers in Pascal's triangle. So to investigate that, if we were to expand x plus y to the power of 6, we would be multiplying 6 binomials of x plus y, and we would get the expansion as follows. Notice that each term in the expansion is a combination of x's and y's. Consider how the third term, 15x to the power 4 y squared, is formed. It is formed by choosing a y from any of the two of the 6 factors in the expansion of x plus y 6. So here we have 6 binomials of x plus y. They're saying that we could choose any two of them. Okay? And also for the x value, we would be choosing from the remaining 4 factors. Therefore, the two y's can be chosen in 6 choose 2 or 15 ways. The 4 x's can be chosen in 4 choose 4 or 1 way. This leads to the term 6 choose 2 x to the power 4 y squared. Write the coefficients in terms of combinations for the expansion below. So again, we have x plus y to the power of 6, and then the expansion. So if we were to write this in combination form, we would basically be looking at these values here: 6 choose 0, 6 choose 1, 6 choose 2, 6 choose 3, 6 choose 4, 6 choose 6, or 5, and 6 choose 6. Okay, so we would have 6 choose 0, x to the power of 6, plus 6 choose 1, x to the power of 5, y to the power of 1, plus 6 choose 2, x to the power of 4, y to the power of 2, plus 6 choose 3, x to the power of 3, y to the power of 3, plus 6 choose 4, x to the power of 2, y to the power of 4, plus 6 choose 5, x times y to the power of 5, and lastly 6 choose 6, y to the power of 6. The expansion of the binomial x plus y to the power of 6 using combinations given on the previous page can be extended for any exponent that is a natural number. This leads to the following general formula for the binomial expansion known as the binomial theorem. So the binomial theorem is x plus y all to the power of n And you can see that the leading coefficients are written in combinations. N choose 0, N choose 1, N choose 2, all the way up to N choose N. Note the general term of the expansion x plus y to the power of n is given by the term n choose k, x to the power of n minus k, y to the power of k. This is called your general term. Okay, n is going to be the number that's the exponent, and k will be the number that we're taking at one time. So for the first example, we need to find the fifth term of x plus y to the power of 8. So just note that k plus 1 needs to add up to 5. Therefore, k has to be equal to 4. And our n is given by the exponent 8. So if we just sub now into the general term equation, we get t k plus 1 equals n choose k, x to the power of n minus k, y to the power of k. Now we sub in our values k and n. T to the power of 4 plus 1 is 5. N is 8, choose k, which is 4. X to the power of 8 minus 4 times y to the power of k, 4. 8 choose 4, if you calculate that, it's 70. And we get x to the power of 4, y to the power of 4. Now, for the middle term of a plus b to the power of 10, note that we always have one more term than the n. Okay, so if we have n plus 1 terms, that means we have 11 terms. Now, if we were to count out 11 terms, the middle term would be the 6th term. Middle term is term 6. So in that event, just keep in mind we have k plus 1 equals 6. So k is equal to 5. And n will be the 10 that we started with. Alright, so subbing into tk plus 1 equals nck, x to the power of n minus ky to the power of k. We get t, k plus 1, so 5 plus 1 is 6. Okay, and then we have 10 choose 5, x to the power of 10 minus 5, so we get 5, and y to the power of k, or y to the power of 5. Now keep in mind, I've been using x and y because that's the formula, but the binomial had a plus b. So term 6, technically, let's just calculate 10 choose 5, that's 252, but x was actually an a, so we have a to the power of 5, and y was actually a b, so we have b to the power of 5. And that's our 6th middle term. Alright, so the next one, we have to use the binomial theorem to write the expansion of x plus y all to the power of 7. So we write x plus y to the power of 7, and starting with 7 choose 0, we'll have x to the power of 7. Perhaps I'll start with the variables and then I'll put the combinations. So keep in mind, x is going to be decreasing while y increases in its exponents. So we have x to the power of 6, y, plus x to the power of 5, y squared, plus x to the power of 4, y cubed, plus x to the power of 3, y to the power of 4, plus x squared, y to the power of 5, plus x, y6, plus y7. Now I'm going to put the coefficients in place, which are represented by combinations. So starting with 7, choose 0, we're going to work our way up to 7, choose 7. So we have 7, choose 1, 7, choose 2, 7, choose 3, 7, choose 4, 7, choose 5, 7, choose 6, and 7, choose 7. So now evaluating these combinations, we would get 1x to the power of 7 plus 7x to the power of 6y plus 21x to the power of 5y squared plus 35x to the power of 4y to the power of 3 plus 35 x to the power of 3 y to the power of 4 plus 21x squared y to the power of 5 plus 7x y to the power of 6, and lastly 1y7. Okay, and I'll just show you where those combinations come from again. This would actually be from the next row. We would have 1, 7, 21, 35, 35, 21, 7, and 1. Or 7, choose 0, 7, choose 1, 7, choose 2, 7, choose 3, 7, choose 4, 7, choose 5, 7, choose 6, 7, choose 7. So we're getting the coefficients from Pascal's triangle and originally from the combinations. So now we're going to apply the binomial theorem to more complex binomials. So Susan was determining the fourth term of 2x minus 5 all to the power of 6. Part of her work is shown below. Complete her work to show that the fourth term is negative 20,000 x cubed. So first of all, it's important to note that in the binomial x plus y to the power of n, our x value is actually 2x. And our y value is actually negative 5. So that's highlighted on the side here. If we're looking for the fourth term, that means k plus 1 equals 4. So k will equal 3, as noted on the side. Our n is given as 6, so we can also note n equals 6. Now using the binomial theorem, n choose k, x to the power of n minus k, y to the power of k, we just sub in what we know on the side. So first of all, k is 3, so let's sub in 3 for k. And then we have n choose k, so 6 choose 3. Our x is represented as 2x from the binomial. And we have n minus k, so 6 minus 3. Our y was negative 5, so that goes here. And that's to the power of k, which was 3. So 6 choose 3, that's 20. Then we have 2x to the power of 3, 6 minus 3 is 3, and negative 5 to the power of 3. So we get 20, 2 to the power of 3 is 8x cubed, and negative 5 cubed is negative 125. So now we multiply 20 times 8 times negative 125, and we get negative 20,000 x cubed. 20 times 8 times negative 125. Yes, that's correct. Okay, good. Now we're going to determine the fifth term of 3x minus 2y to the power of 7. So first of all, let's just note what we have. X is 3x. Y is negative 2y. Our n is 7. And we need to find the fifth term. So k plus 1 will equal 5, which means k is 4. General term is represented by tk plus 1 equals n choose k, x to the power of n minus k, y to the power of k. So we have term 5 equals 7 choose 4. Our x was 3x to the power of n minus k, so 7 minus 4, times y, and our y was negative 2y, to the power of k, so to the power of 4. 7 choose 4 is 35, and then we have 3x to the power of 3 and negative 2y to the power of 4. 35 times 27x cubed times negative 2 to the power of 4 is positive 16, and y to the power of 4. When we multiply through, 35 times 27 times 16, we get 15,120, and then we have x cubed, y to the power of 4. Applying the binomial theorem where k is unknown. Alvin has been asked to solve the following problem. One term in the expansion, x squared plus a all to the power of 8, is 114,688 x to the power of 4. We need to figure out what is the value of a. Alvin does not know how to proceed because he does not know which term he is looking for. His friend Griffin explains how to determine the value of k by showing him the following work. First of all, we note that x is actually x squared. Our y is actually a. Our n will be 8 from the exponent. Okay, and then k is our unknown. So first we need to write out the general term and choose k, x to the power of n minus k, y to the power of k, and then fill in what we know. We have n is 8, so we replace all the n's with 8s, and then we can replace our x and our y with x squared and a, x squared and a. Then we can expand, so we have t of k plus 1 equals 8 choose k, x to the power, expanding the exponent, we get 16 minus 2k, and a to the power of k. So since the term we are looking for contains an x to the power of 4, okay, recall one term in the expansion is 114,688 x to the power of 4, we can determine the value of k that satisfies this condition. So keep in mind, x has to be to the power of 4. So we're looking right here. We have x to the power of 16 minus 2k, but it should be an x to the power of 4. So given that we have the same base, x and x, we can set the exponents 16 minus 2k equal to 4. So 16 minus 2k equals 4, and then we just solve for k. So when we do that, we get 16 minus 4 is 12 equals 2k, and k equals 6. Good. So now, let's write out what we know. Okay, k is actually equal to 6. So we have y is a, x is x squared, k is 6, and n is 8. So tk plus 1 equals n choose k, x to the power of n minus k, y to the power of k. We get then tk plus 1 is t6 plus 1, or t7. That will equal 8 choose 6, x to the power of 8 minus k, so 8 minus 6, multiplied by y to the power of 6. 6 choose 8, we get 28, and then x to the power of 2, and y to the power of 6. Now keep in mind, our x and y's were not actually x and y's, they were x squared and a's. So let's just replace our x with x squared and our y with a. So we have 28 x squared to the power of 2, and y was actually an a, so a to the power of 6. So we get 28 x to the power of 4, a to the power of 6. So for the next one, we have to equate tk plus 1 with 114,688 x to the power 4 and solve for a. So we know that term 7 is equal to 28 x to the power 4 a to the power 6. So we're just going to set that equal to 114,688 x to the power 4. The x to the power 4s can cancel out. And then we can divide by 28. And we get a to the power of 6 equals 114,688 divided by 28. And we get 4,096. Taking the 6th root of that, we then get positive and negative 4. Now, one thing to note is a has to be positive, as we read here. Therefore, a can only equal positive 4. Determine the numerical coefficient of the term containing a to the power of 7 in the expansion of 3 minus a all to the power of 10. So let's just write out what we know to start with. Tk plus 1 will equal n choose k, x to the power of n minus k, y to the power of k. Our x given from the binomial is actually 3. Our y given from the binomial is actually negative a. Our n is 10. And our k is k. We have to solve for k. And we're going to figure out what k is by looking at a to the power of 7. So let's write out what we know so far. Tk plus 1 equals 10 choose k. Our x was 3, our n is 10, we don't know k, and our y value was negative a to the power of k. Expanding further, 10 choose, we know that we need to have a to the power of 7. So looking here, a has to be to the power of 7, that means that k has to equal 7. So we can just sub in k as 7. So we have t7 plus 1 equals 10 choose 7, 3 to the power of 10 minus 7, negative a to the power of 7. 10 choose 7 will be 324. Times 3 to the power of 3. We can split this up, and that will be like negative 1 to the power of 7 and a to the power of 7. So once we multiply through, sorry, that's just 10 choose 7. Once we multiply this through, we get negative 3,240 times a to the power of 7. So when asked to find the numerical coefficient, it's simply negative 3,240. For the final example, we need to determine the constant term. For example, the term independent of x in the expansion of 2x minus 1 over x squared to the power of 15. So let's just write out what we know again. The general term is t, k plus 1 equals n choose k times x to the power of n minus k, y to the power of k. Our x value is actually 2x. Our y value is negative 1 over x squared. Our n is 15, and k at this point is k. So subbing in what we know, we have tk plus 1 equals 15 choose k, 2x, 15 minus k, multiplied by negative 1 over x squared to the power of k. We can separate the variables from the constants, and we get 15 choose k, 2 to the power of 15 minus k, x to the power of 15 minus k, negative 1 to the power of k, and if we just take the reciprocal, we get x to the power of negative 2 to the power of k. So putting the coefficients together, we get 15 choose k times 2 to the power of 15 minus k times negative 1 to the power of k, all multiplied by x to the power of 15 minus k and x to the power of negative 2k. I'm just rewriting the coefficients. And you can see that we have a common base of x, so we can just add these exponents. So we get x to the power of 15 minus 3k. Now they told us that we're looking for the constant term, which means that we need to have x to the power of 0. So if we should have x to the power of 0, then that means we can solve for the k value by setting them equal. So set the exponents equal, we can then solve for k. And k equals 5. So now we can replace that back into our general term. 15 choose 5, 2 to the power of 15 minus 5 times negative 1 to the power of 5, and x to the power of 15 minus 3 times 5. So you should get an exponent here of 0. If you don't, then you solved for k incorrectly. Now multiplying through, 15 choose 5 is 3003. 2 to the power of 10 will give you 1024, and negative 1 to the power of 5 is negative 1. And again, you should have x to the power of 0, which is just equal to 1. So 3003 times 1024 times negative 1 gives you negative 3,075,072. And we found our constant term.